This is an example of an AC analysis problem in Circuit Tutor on level 4, and in particular this is the third type of problem, which is a Thevenin-Norton equivalent circuit. So let's begin by looking at an example of this type of problem that illustrates many different solution methods. So you can see we are being given a problem here in the phasor domain, as we have complex impedances and phasor values for the voltage source. And this has a set of terminals which are going to be used to connect to some arbitrary circuit. And we have labeled on there an output voltage V with the indicated polarity and an output current I with a corresponding polarity that constitutes the active sign convention with regard to whatever is going to be connected there. So our goal is to take this circuit, which has 1, 2, 3, 4, 5 elements in this case, and convert that to a Thevenin and a Norton equivalent circuit, each of which will have only 2 elements, namely a voltage source in series with an impedance for the Thevenin case, or a current source in parallel with an impedance for the Norton case, the same impedance in both cases called Z Thevenin. So to do that, there's a number of different approaches we could use. The easiest method in general here will be to do source transformations and to combine elements in series and parallel. For example, there's 2 elements in series. That's nearly always the easiest method, but there are several other methods that are illustrated here, and all of these different approaches are summarized here. So for example, this shows you what you could do as far as the source transformations approach. So here the J4 inductive impedance and the 6 ohm resistance have been combined into a single element Z1, which is just 6 plus J4, just adding those values. And notice that that has been changed from resistor symbol into a generalized impedance symbol, because this is a fully complex number and that is not compatible with a resistor symbol. So we need to use a new symbol there to be correct. Having done that, then we can no longer combine anything in series or parallel. And one thing to point out is that when you have terminals, do remember that if, for example, if this happened to be a passive element, it would not be in series with this one. And the reason is that these terminals imply that we have some sort of other circuit connected out here, which means that current will flow. That's why, of course, we have the I symbol down here to remind us of that, is that there in general will be an output current unless these happen to be open circuited, which would be unusual. So because there is a current, say, going here, coming back here, these 2 elements will not have the same current. They are not in series, and it's very important to remember that whenever you have terminals present in a network, as we originally discussed in the series parallel with terminals tutorial. Okay, so because there's nothing in series or parallel here that we can combine, what we can do is to do a source transformation. So here we have a voltage source in series with an impedance, and just like we can do for DC circuits, and we've done in the other problems at this level, we can transform that into a phasor current source in parallel with the same impedance. And that's shown down here. And the diagram has been expanded a little bit to make room for doing that, so it's been kind of stretched out, if you will, without changing any connections. And notice that we now have a current source in parallel with the capacitive impedance that used to be a voltage source in series with that. They're still connected between the same 2 nodes, the one that go to the negative terminal here, which is this one, and the one over here on the right side, which again, these were connected to, the series combination was connected to here. So these are still connected between the same 2 nodes that they were before, which is what it should be. And now for the value of I1s, we would have to compute that by dividing V1s by the impedance. Now that doesn't really even require a calculator here, because the V1s is just 3 angle 0 is the same as 3, and dividing by negative j, or negative j1, the same thing, that's the same basically as multiplying by j, because you have to remember that 1 over negative j is j, because j squared is negative 1. So therefore, we're just really multiplying this by j, and so that would become 3 angle 90 degrees, because remember j is 1 angle 90 degrees in polar notation. So, and you can remember that from the Argon diagram. If you were to draw the unit circle in the complex plane here and plot the point J, that would be up here above the origin along the imaginary axis, and it would be basically an angle with respect to the positive real axis of 90 degrees. So, okay, so we've computed that, and then the polarity we have to check carefully. So the head of the current source now matches the node that was indirectly here connected to the positive side of the voltage source, and the negative to the negative and to the tail. So that's the correct polarity, and the computation is shown here. And then we now have these two things in parallel, and we can combine impedances in parallel. So we remember that to combine two impedances in parallel, or any number really, you take the reciprocal of the sum of the reciprocals of the individual impedances, which would be these numbers here. And of course those could really be computed in your head as 0.25 plus j, so we have to take the reciprocal of that, and that works out to this value when you do that on a calculator. Okay, so that's the equivalent impedance, which is now denoted Z2 on the diagram, is indicated down here. And notice these are all being given to 4 significant digits, and it's really a good idea to have significant accuracy here, because it's easy to accumulate round-off error, especially with complex numbers where there's an extra degree of freedom when you're doing multiple repeated calculations. So it's a very good idea to keep at least 4 digits, and maybe you want to use the full precision of your calculator really for those intermediate results would probably be a better idea yet. And that way you won't have any problems where it's rejecting your answer due to accumulated round-off error, which might be very frustrating. Okay, so we've done that, and then we need to do one more source transformation. We now have a current source in parallel with impedance. Notice that these are not either in series or parallel because of the presence of the current source. So we do that, and we change the current source to a voltage source here, and notice the polarity matches the head of the arrow to the plus side. And then we moved the impedance from being in parallel with the current source to being in series with it, which a convenient place is to put it up here. And so now we have this impedance, the same impedance we had before. And of course, to compute that V2S, we needed to multiply I1S times Z2. So the 3 angle 90, or 3J equivalently, multiplies this. And that's probably easiest to do on a calculator. And that would give you the value of V2S as shown here. Okay, and then finally we would just combine those two impedances in series by adding their values, which is fairly simple to do. That gives us this new impedance Z3, which is this value down here, which is the sum of the two original impedances. And now you notice this is the form of a Thevenin equivalent circuit because it has only 2 elements consisting of 1 voltage source and 1 impedance that are in series. So that is a valid Thevenin equivalent circuit. And remember that they never have more than 2 elements. Okay, now there's several other approaches we could take. For example, we could find the open circuit voltage. And of course, if you wanted to get the Norton, then you could just do a single source transformation on this, which will be done at the bottom here. Now, if you wanted to take an alternate approach, you could find VOC by replacing the terminals here with an open circuit voltage, which is now a SOT variable across those terminals. And in this case, if you look at the circuit, there's no current that can actually exist here in Z1 because it's dangling. It's not connected to anything out here. So therefore, the only current is going to exist in this loop here. And therefore, that's really just a voltage divider, if you think about it, a single voltage source in series with 2 impedances. So we can use the voltage divider formula directly here with the value of the source, the 3 angle 0, and then we take the impedance of interest, whose voltage we want to know, the 4 ohm, divided by the sum of those two. And remember that the VOC will consist basically only of that voltage because there is no voltage drop across an impedance that has no current, because that's a dangling impedance. So it's essentially redundant as far as the VOC is concerned, at least. And so also we have to check the polarity. So the positive side of the source corresponds to the positive side over here, and that does match up with the positive of VOC. So that means we're going to have a plus sign here. The negative of VOC matches with the negative side of the source. So we will have a plus sign here. Remember, it could equally be a negative sign, and often is. So now we just compute that, and that would give us the VOC value. Now an alternative would be, instead of putting an open circuit here, to replace the terminals with a short circuit. And now we would have this be ISC by definition, which flows in the same direction essentially as the original I. Remember, that came out here or went back in there. And so that's the correct direction. Now this circuit actually is not a single loop or single node pair, so it requires a full-blown mesh analysis, which is illustrated here. So that probably is not the easiest way to solve this problem, but it could be done if you wish to do that. And it'll, if done correctly, of course, it'll yield the right answer for ISC. Now, the third parameter we could calculate, remember that we basically need any two of those three parameters, the VOC, the ISC, and the ZTH, because remember, VOC is equal to ISC times ZTH, similar to Ohm's law, basically. And so any two of those are really sufficient, although we could use the third one perhaps as a check. So to find the Thevenin equivalent impedance, we would take that V1S voltage source that was originally there and change that to a short circuit, in other words, a zero-valued voltage source. That's been done on this diagram. And then we would basically look into those terminals to see the remaining impedances and see what the total impedance is there. So that's a very simple problem, similar to ones you've done before in impedance simplification. And here we have to combine these two in parallel. Remember, you don't just add all three because they're not in series after all, right? These two are in parallel, not in series. So we have to combine those in parallel. And that would require use of the reciprocal formula, 1 divided by the reciprocal of each of the impedances, the sum there. And computing that, as we did in the other source transformations, we'd get this value. And then those two impedances now have to be added, and that would yield the same value that we got from the Thevenin, from the source transformation method. So that's kind of a check on that. So no matter how you do it, you're going to get the same final Thevenin equivalent circuit here, which has the one voltage source and the series impedance, and then the I and the V are labeled on that properly. And the VOC and the ZTH came from the above calculation, whether we did source transformations or the direct computation of VOC and Z Thevenin, or perhaps we found ISC and divided VOC by ISC to get Z Thevenin. There are various ways of getting those. Then one more source transformation on this, we change that to the voltage source in series with impedance to a current source in parallel with the same impedance, the same value of Z Thevenin, which doesn't change. And so we want to make sure that the polarity is consistent. So again, we have the positive side of the voltage source matching the head of the current source here, which it does. And then to find the value of ISC, we would simply divide VOC by Z Thevenin. So we divide this complex number by this one using a calculator in that case, and that would work out to this value of ISC. And that would basically complete the problem. And you could also, if you did those three parameters by independent methods, then you could check that they do in fact satisfy this relationship, that VOC equals ISC ZTH, and that would be a good check on all the previous calculations. So that's a good method to use. For example, if you're doing this type of problem on an exam, you could, if you have time, you could calculate it multiple ways and check that they actually agree, which would give you a high degree of confidence in your result. Okay, so let's go now and do an actual exercise at this level. And this type of exercise again with Thevenin and Norton. So we are being given again a problem in the phasor domain, because the complex impedances and the complex value of the sources, that shows us definitely we're not in the time domain. There's no t variable to be found here. So the easiest approach, again, to find the Thevenin equivalent of all this circuit here would be to do source transformations and simplifications. So we're going to go into the circuit editor to do that. Now, we do have other alternatives. If you would rather do a different method for some reason, you could click on Find VOC, and then you would basically, it would automatically change this to a sought voltage here on the output terminals and set I equal to 0. And then you could go through whatever analysis method you want. Probably you'd want to do a single loop analysis, since there's only one place that current can actually exist in this circuit, and then deduce the voltage across the 3 ohm, remembering that the voltages here and here are going to be 0, because after all, this is open circuited, so no current will exist in those elements, and therefore no voltage drop either, since V equals IZ. So that would be a way of finding VOC, or we could click on find ISC, in which case it'll automatically put a short across here for you. In that case, the ISC would point down consistently with this direction of I. And then you'd probably, in that case, have to do a mesh analysis to find ISC. And that might be a little bit more complicated. Or you could use nodal analysis also. You'd have your choice of methods here. It would allow you to do either mesh or nodal analysis, although I'd probably be inclined to do a mesh analysis there. And then lastly, you could also find the Thevenin impedance directly. And remember, if you do that, then you have to remember to kill this source. Before you do anything else, you would want to change this to a short circuit. And in other words, a zero-valued voltage source. And that would put these two elements in parallel, which you could then combine with the reciprocal formula. And then you could add the resultant to that to these other two values, and that would give you the total Thevenin impedance seen from the input terminals looking in over here. So those methods will all work, and if you did any two of them, then you'd have enough information to get your circuits. But as I said, I would prefer to just do the source transformation method because I do think it's more efficient for this problem. So let's do that. Okay, so now the first thing I'd like to do is to combine these two elements that are obviously in series, the 6 ohm and the J1 ohm. So let's just add that, and I'll just make the 6 become 6 plus J1. Don't need a calculator for that. Or 6 plus J really is good enough. Now notice that that's red, and the reason is that a resistor cannot have a fully complex value. So I need to change the symbol that I'm using there to be a generalized impedance, and that's actually explained down here. So I've changed that, and then I want to change this to a short because I've basically subsumed that impedance into this one, and I don't want to duplicate. And of course, it wouldn't be an open circuit. That would leave my whole circuit open, which wouldn't make any sense. So I check that, and that is correct. And now it shows me the last valid step that I took. And now you might say, well, are these two, for example, in series? But you have to remember that even though they might look like they're in series, they're not, because there is some current I. We're going to connect something out here. That's the whole reason of making this equivalent circuit, is so we can connect it to something. And therefore, there will be a current I here, which means that these two things will not have the same current as they would if I were 0. So unless we're doing open circuit voltage, these things are not in series. Okay, so because of that, we cannot combine those, and we can't combine really anything else here. So now we need to do a source transformation. So I want to change the voltage source in series with this capacitance into a current source in parallel with the same capacitive impedance. So to do that, I'm just going to move this out of the way here, and I'm going to drag this up into position here, and then I'm going to move this over here and move this up here so that I put them in parallel. And then I need to add some more wires to reconnect everything. So I go to Add New, and that will automatically select a short for me here. So I can just connect there, and I click there, and I click here, and that will reconnect everything properly for me. Now I need to actually change this to a current source, which I haven't done yet. So I'll click on the current source. I want to make sure that I have the arrowhead on the same side and connected to the same node, basically, that the plus side was. And that's correct by default, although it isn't always going to be like that. And now I need to compute the value of this current source. So I need to divide this voltage by this impedance. That's probably not so easily done in my head. I could figure out the magnitude, but not the... well, no, actually, I could do that in my head, because 2 divided by 8 is 0.25. So let's just do it that way. And then minus J8, that corresponds to a phase angle here of negative 90 degrees. So if I take this and divide by negative 90, that means adding 90. So that would give me 60 plus 90 is 150 degrees. So if you're not comfortable, you can always use a calculator, but in this case, I can save doing that by doing it in my head or on paper. Okay, so let's check that. And that is correct. And now I have two impedances that are in parallel. So I can combine those by using the product over sum formula. So that would basically be negative 24j divided by 3 minus j8. Well, I can't do that in my head, so let's go get the calculator. And I'm using a TI 8384, well actually it's an 84 plus emulator to be precise. Now I'm going to want an impedance, so I'm going to want that in rectangular form. But before I do that, I was just going to show you how I define this variable e. So on this model in particular, I must be in radian mode to do this, because this will not accept this expression if it's in degree mode. That depends on which specific software update and so forth you have as to whether or not it'll accept that. But here I basically entered e to the I pi over 180. So why did I do that? Well, basically, if I raise that to the power of an angle in degrees, that'll multiply the exponents. And so that will basically convert the exponent from degrees into radians. And remember that this complex exponential function on this model of calculator, 83 or 84, requires that you always put this in radians, even though you may be in degree mode up here. So in other words, Euler's identities don't work in this calculator, which is rather curious. But it's a particular peculiarity of this calculator. In the 89, it's more rational, and you would not have to worry about that. But in this model, I'm going to do that. So I'm just going to enter that to store that in the e variable that would be here. And having done that, then I'm going to change my mode now. And now I want to be working in degrees, first of all, because that's what I normally want in Circuit Tutor. So I'm going to go, and that's what engineers probably use more often anyway. So I'm going to use degrees. And then I also need to go down, and I want, for this particular calculation that I'm doing right now, I need to, I want the answer to be in rectangular form. So I'm going to select that just so I don't have to do a conversion at the end. So there I have that, and now I can exit that, and I just verify I'm in rectangular mode in degrees. Okay, the degrees won't, well, actually it will matter for, well, no, it won't matter here, but it will matter in future calculations. So now let's do this calculation of combining these two things in parallel. So remember, in parallel, I have to take the reciprocal. So I'm going to take 1 divided by the parentheses of the denominator. Now, you could try to use the n/d templates that this calculator does, but those don't always work for complex numbers depending on which model exactly you have. So I would recommend just doing it this way using the division key. It's probably easier. So now I need to have the reciprocal of 3. So I could write 1/3, or I can just go 0.3333 for some accuracy. And then add to that the reciprocal of negative j8. And again, I could do that in my head and say, well, the reciprocal of 8 is 0.125, exactly. And then the reciprocal of negative j is j, because remember that j squared, by definition, is negative 1. So that would just be j, or on the calculator, it's denoted I. So that's just an easier way to enter that. But you could also write it as the reciprocal inside there, but you'd have to use more parentheses. So I just did it this way to make it simple. Okay, so let's evaluate that. And that gives us this answer. So I'm going to enter that here as 2.630. I'll just leave 2.63 minus j times 0.9863. So make sure I've got enough accuracy there. And notice that that's now red because that fully complex value is not compatible with the capacitor symbol, so I need to change that to a generalized impedance. Okay, so now it's no longer red, that's correct. And I also need to delete the 3 ohm that was basically combined into that, so I change that to, just by deleting it, basically change it to an open circuit. So now let's check that combination, and that is correct. And now you see I still don't have a Thevenin or Norton because I have 1, 2, 3 elements, and I'm only allowed to have 2 elements in such a circuit. So I need to do one more source transformation. So I'm going to change this into a voltage source now. And notice that the polarity actually happened to come out correct here because the head of the arrow where it used to be now corresponds to the plus sign. So that's good. And then I need to also move this in series. But before I do that, I think it's going to want me to enter this value. So now I need to multiply this times this because V equals IZ. And that certainly we can't do in our heads, so I'm going to get the calculator here. And now I want the, since I'm computing a source value, I'm going to want that in polar form. So I'm going to go into the modes, because right now I see I'm in rectangular form from the last calculation. So I'm going to switch that back to polar form real quick. And that way I won't have to convert it at the end. It'll just be easier. Okay, so now I'm going to multiply the 0.25 and then E150, so that's where I'm going to use that E symbol that I defined earlier to the 150 power. And notice this works because I'm in degree mode now. And I'm going to multiply that times the impedance. So I'll put that in parentheses because by order of operation, of course, I have to be inside parentheses here, or I'd only be multiplying by the first number, and that's not what I want to do at all. So that minus I times 0.9863. And just check that that's all correct. That looks good, so I'll press enter. And so that should be the value of my new voltage source. So I'm going to enter 0.7022 for accuracy's sake there, and then this will be 129.4 degrees. And now I also need to move that impedance to be in series with the voltage source, because otherwise I wouldn't have done a source transformation properly. And I check the polarity is correct, and everything is connected. Okay, so that should be all good. So I'm going to check that. And that was correct. So now I have one more step to do, which is to combine these two impedances. And oh, I guess I may want a calculator for that. I could probably do it in my head, but I'll just do that as a calculator. So I'm going to add 6 plus j, and let's see, I want this now in rectangular form, however, so I have to change that back. So I'm going to go 6 plus j, which is I, plus 2.63, oops, not plus but minus, so it's minus I times 0.9863. Of course, it doesn't matter whether the I comes before or after because multiplication is commutative, so that's all fine. So that gives me the result. The 8 plus 6.3, I kind of knew that, but the other part is a little bit harder to do, so I'm going to change that to plus j 0.0137. And then I have to change this one to a short circuit by clicking over here. And now I do have a valid Thevenin form because I have a single voltage source in series with a single impedance. And so that should be valid. So let's, well, first we have to check the combination though. So let's do that. And then we are allowed to check the Thevenin equivalent now that we have a Thevenin equivalent. So let's do that. And that is correct as we heard the ta-da sound. But notice it is commenting to us that the value of this voltage source is actually not VOC. And the reason is that the positive side of this source happens to be connected to the negative side of the output voltage and vice versa. The negative goes to the positive. So this is actually the negative of VOC. So when it's printed VOC up here for me, it's actually, as you may notice, the phase angle has changed. That's because it's subtracted 180 degrees from this value. And that's basically because multiplying by a -1 to change the polarity is the same as multiplying by one angle 180 degrees, because that's the polar form of -1. Remember, in the argon diagram, the -1 would be over on the left here, to the left directly of the origin. So it would be an angle of 180 degrees. So subtracting 180, you want to keep always the angles in the range from -180 to plus 180. So here we want to subtract rather than add. But of course, you can do either one because it brings you around to the same point either way. Okay, so that's just pointing that out, is why VOC is not that value. Okay, so now it wants us to do the last transformation, which is one more source transformation. So I could just change this to a current source now. And it does have the head where the other one used to be. And let's see, I got to go capture that. It's gotten moved off here. Now I need to divide the VOC by the Z Thevenin. Or actually, I'm not dividing VOC, but I'm dividing the value of the source as I've written it, since if I want to keep the current source pointing consistently with this one, which is probably the most straightforward thing to do. So now I need to divide those two numbers, again using a calculator. So now we're going to take 0.70, 0.7022 divided by parentheses. And let me also check that I'm in the right mode. So in this case, no, I want to be in polar mode. So I'm actually going to interrupt here and go back into polar mode. I can do that in the middle of it. Before I compute the answer. And I'll have to come back over here. Okay, so 0.7022 divided by that 8.63. And again, it has to be in parentheses here, plus I times 0.0137. And close parentheses. And that matches what's printed on the screen up here, which has a little bit more accuracy than what I can see right here. And so we enter that, and that will give us the value of our current source. So that's going to be 0.08137. And the angle is very small. It's negative 0.091 degrees. Okay, and then I also need to put this in parallel with that current source now. So I'll drag it down here, and then I'm just going to add an extra wire. This may not look like the way we normally draw a Norton source, but of course it is equivalent because, I have them both connected in parallel with the output. So that should be fine. I've got the polarity correct, and I believe everything should be good. So I'm going to check that source transformation. Okay, so it doesn't like my value, so let's see what happened here. So 0.7022. Oh, I simply forgot the angle. Okay, so I made a silly mistake there. So I'm just going to go back and patch that up here. So I'm going to go into insert mode here and go with my E to the power negative 50.6. So that's much better. I should have checked that more carefully before. Okay, so now we click enter. And so now we'll correct this value. So that should be, well, the magnitude, yeah, it's just a phase angle change. So the phase angle, and that's why that phase angle came out so small, actually, is it was just incorrect. So that's negative 50.69. And let's try that now. Okay, so it's telling us the polarity of the transform source is incorrect. And indeed, because I used the VOC value, and again, that was the wrong, I should have been using this value. So I made another mistake. So what I can do is to simply fix that is I'll just change the polarity. That's the easiest way to fix that rather than bothering to change the angle, and that will fix it. Okay, so it's perhaps good to see that I make some mistakes here, because that's quite possible to do in these problems, but we still managed to complete it. And now this is a valid Norton equivalent, so all we have to do is click the button that checks that. And that basically means we're done. We just click the complete problem button. We have the parameter values here, and this is showing us the Norton equivalent. And if you wish, you could get the complete explanation similar to an example here, but I'm going to skip that for right now. So that completes the problem.